already talked about, of course, kinematics is the study of motion. And you notice on the top of page 53, you see your kinematic equation, kinematics equations. And how on God's earth do they come about those equations, okay? Well, the first one, 2.10, if you remember from basic, plain old simple, there it goes acting crazy, plain old simple definition of acceleration. If you recall, that first equation, acceleration is equal to what? The rate of change in velocity per time interval. The change in time interval. So we can break that down, y'all. We know that whenever we see a delta sign, it's that right there. Okay. And then, of course, we can rearrange the equation to say what? VF is equal to what? VI plus AT, right? So there's your first kinematic. So that one doesn't really need derivation. That just comes from the definition of acceleration itself. That's where it comes from. Acceleration is defined as the rate of change in velocity, y'all. Okay? All right, now, but what about these others? What about these others? Let's look at that second one. Okay? Let's look at the second one. If we were to graph, well, I'll tell you what, no, let's not look at the second one yet. I'm going to jump down to the third one, 2.13, and then we'll come back to the second one in a minute. Okay, yeah, I know I'm being a pain. All right. Okay, let's look at the third one, 2.13. Where does that one come from? All right, if we graph velocity, and we graph time, just like this right here. Okay, y'all. And remember, y'all, whenever we have constant velocity, it's going to look like that on a graph, isn't it? Right? If the velocity is not changing on a velocity time graph, it's going to look like that right there, isn't it? Okay? What is this area right here going to give me? What would that give me? I hear some of you saying it under your breath. That forms a rectangle, right? What's the area of that rectangle going to give me? What's velocity times time going to give me? All right, y'all remember your 9th grade physical science? No. That's okay. That's why you're here. All right. Okay, remember this little 9th grade equation? Remember how to find the velocity, the average velocity? It's change in x over t. So if I want to find x, and you could actually say constant there. So the area of that rectangle is my displacement. Do what? Yes. The area of that rectangle is the distance I have traveled. Come on, y'all, think about it. If I set your cruise control to, I was going to say 75 miles an hour, that's break. Well, no, it's not. What's the speed limit on it? Ooh, it's 70. Yeah, okay. I'll say 70 because I just went to driving school, and if Randy Amos heard me say 75, he'd come hunt me down. Sorry, Randy. Officer Amos, excuse me. 70. All right. 70 is the speed limit on the interstate. All right. So set your cruise to 70. I saw him at the funeral home the other day. He says, "You driving safe?" I said, "Yes, sir." I ain't gonna lie. I was. I'm tired of tickets. Okay. I told my wife, I said, "Here," I threw the keys at her. I said, "I'm not driving anymore. Here, you drive." All right. So, think about it, y'all. Set your cruise to 70. All right, y'all, that's constant speed. You clock the time, provided you don't change that speed, If you drive 70 miles per hour in 1 hour, how far did you travel? 70 miles. Okay. All right. Now, well, that's all great, fine, and wonderful. But what happens if we accelerate? Oh my goodness. Well, now we've got to do what? Now we've got more displacement in there, don't we? Yes, Mr. Shields. Okay. So how in the world do we find that? Okay. Well, now we've got a right triangle, don't we? Huh? And we're going to call this right here the initial. Yeah, gummit. I can't write with a hoot. All right, we're going to call this right here. Hello. Please write. Get on the pen. That's V initial, and that right there is V final. Okay? Now we've already said this is displacement. That's delta x. Okay? So, how do we find that? Well, we know then that the area of a right triangle is what? The area of a right triangle is 1/2 the base times the height, right? 1/2 the base times the height. Correct? Well, first of all, let's establish what this area is. Well, we've already established that to find our displacement, let's establish what we know. To find our displacement, it is the what? The initial velocity right here times the change in time. So VI times delta T. That's this right here. Okay? We've already established that. But we want to find it. We want to find what? We want to find what? We got to find it here. Okay? It's 1/2 the base times the height. Now we're going to come back to this right here. Okay? We're going to come back to this right up here at the top here in just a second. Okay, y'all. Well, what is the base? Or excuse me, what is the height? 1/2? 1/2 the base times the height. Or 1/2 the, let's say 1/2 the base times the height. Okay. Our base is time, okay, times the height, okay. So, we've got 1/2. Let me write it right up here. Our base is what? Time, delta T, and what's our height? Alright. VF minus VI delta T. Okay, y'all, do you see something jumping out at you there? Notice this right here is the same thing as this right here. Acceleration. And so we substitute and it becomes 1/2 A delta T or T squared. And so we come back down here and we substitute her in 1/2 AT squared. Okay? And there Now, I know you're saying, wait a minute, it doesn't look like that in the book. Well, look, y'all, delta x is x final minus x initial. Move the x initial over to the other side, and it becomes x initial plus vi delta t plus 1/2 at squared. Now, let me show you something else. So you can do that. Whoops, sorry. You can do that right there. X final. Let me erase that. I'm sorry. That's messy. It's messy. Sorry about that. Okay, now watch. X final. You can do it that way too. Delta x, you can break it apart and do that right there. Now let me show you something else right here. I'm not going to write it, but I'm going to point. Watch. What about this part of this triangle right up here? What if we did this right here? And we wanted to find, instead of finding using initial velocity, what if we used final velocity? See, that's using initial velocity. See, this is going from here to here. What if I wanted to use final velocity instead of initial velocity? In other words, what if I didn't know my initial velocity, but I knew my final velocity? What would I do? I'd cry. No. Because trust me, I've cried in college. I know some of y'all think, oh, I can't believe that. Oh, yeah. A time or two. I ain't gonna lie, I might as well just be honest. True men cry. Guys. Say, true men don't marry good-looking women. Hey, you see my wife, you'll change your mind. Bless God. Anyway, if you don't believe me, go over to the basement of the... No, don't. You leave my wife alone. She's good-looking. She's GED chief examiner, I'll say that. Anyway, all right. Okay, enough of that. Teach, right? Okay. You gotta have a little humor, guys, because I know this is like, all right, okay. All right, what do we need to do? I done forgot what I was talking about. Oh yeah, okay, right here. You got my mind on sweetie. Oh yeah, okay, all right, okay. Final, you crazy thing, all right. Final velocity, put a VF here, VF, and what's going to happen right here? Instead of adding, I need to do what? That's right. Subtract. Now, I'm not going to write it. You can write it. Just make a little mental note. Mr. Shields said if I don't have initial velocity and have final, put VF here. Okay. And change that to a negative. Okay. And change that to a negative. Okay. All right, there's number 3. All right, what about number 2? Okay. What? I know what I did. Crazy me started at the, there we go, at the end instead of the beginning. Okay? Look at number 2. How in the world do we come about that one? Okay. Go back to the same graph. Now, by the way, that is the definition, or excuse me, the solution of velocity, finding the position as a function of time. The first one was velocity as a function of time. That one was find position as a function of time. This one is the position as a function of velocity and time. So we've got both velocity and time. So this one is velocity and time. That last one was position. You can write this down. This is on page 53. I mean, you can write it down. You can add it to your notes, page 53. Now, this one is the position of velocity and time. How do we come about this one? Okay. We've got velocity. All right, we've got initial here. Okay. And we've got delta t down here. All right, I made that a little bit too long. Whoops. All right. Okay, I'm going to do this. And I'm going to go up here like this. Y'all, that's a trapezoid. And the definition of a trapezoid, to find the area of a trapezoid, it's what? You add the two sides and do what? You add the two sides, divide by 2, take the average of the sides, divide by 2, and multiply by the base, right? Definition of a trapezoid, right? So, we know, y'all, we already know that this is delta x. We already know that. because the velocity times the time gives us displacement. So, by the definition of a trapezoid, y'all, this one's easy. And we are done. We are done. And that's a plus, by the way. That's the definition of a trapezoid. Okay, definition of a trapezoid. We are done. Now again, I know it looks a little different what's in the book. Remember, y'all, you can expand that to say x minus xf minus xi, move the xi to the other side, and make it 1/2 instead of divide by 2, same difference. Okay, all right. All right, but what about the last one? The last one's going to make us scratch our head a little bit. Okay, y'all, let's go to that equation, this equation right here, where we defined acceleration, okay, where we defined acceleration and solve for time, because if you'll notice on the last one, it's the velocity as a function of position. Notice we've got to get rid of time. Well, how do you get rid of time? Well, you set an equation equal to time and then go into another equation and substitute into that equation so you can get time out of that equation, right? It's called substitution, okay? You substitute. So you got to set one of your equations equal to time and then substitute that into another equation, okay? So we're going to do that. You know this. You know that. I mean, y'all are math geniuses, all right, now. Right? And which one are we going to pick? Okay, let's take this one. This one right here, the one we just had, delta x is equal to VF plus VI over 2. And why are we picking this one? Well, because it has time in it. And it only has time in one location. It has time, you see what I'm saying? It doesn't have time on two different variables. It has time, there's one variable for time, in other words. One delta t. It doesn't have it on initial and final. You see what I'm saying? It's the whole quantity. It's on the whole quantity, not on just one or the other. Okay? Makes it a little easier to work with. Alright? So we substitute. And I think you see where this is going. Whoa! Alright. And we just do substitution. And it becomes what? It's VF plus VI over 2. And then you're going to substitute what? Times VF minus VI over A. And what do we call it? Is that the difference of squares? Is that what that ends up being? And it becomes this. Delta X is equal to what? If that doggone thing, I keep hitting the button on this. All right, that becomes VF squared minus VI squared over what? 2A. And it becomes what? It becomes what? It becomes 2A delta X is equal to VF squared minus VI squared, or VF squared is equal to VI squared plus 2A, that's an X, not a T, X, 2A delta X. And there you go, no time. So there's your 4 kinematics, algebraically. Okay? Real simple derivation. Okay? Real simple. Real simple. Okay, now let's do it with calculus. Now, do understand this. Notice on page 53, this says under constant acceleration. Okay? This is under constant acceleration. Now, this does not necessarily mean that you cannot use these if it's not under constant acceleration. You just got to realize something. You've got to know whether it is constant acceleration or whether it's not. Okay? And that's very important to keep up with. It's very important to keep up with. Okay? And it does make a difference. It makes it a lot easier if it is constant acceleration. Okay? Or if it's constant velocity. If it's constant velocity, acceleration is 0, we don't have to worry about acceleration. Because guess what? If it's constant acceleration, that A term's gone. And whatever's attached to it's gone. All right, let's do calculus real quick. All Alright. Let's derive that first one we did, the first equation there, 2.1. Again, going back to acceleration, if we use calculus, we know that acceleration is found by taking what? dv over dt, right? Remember that acceleration comes from the what? We find acceleration by taking the first derivative of the velocity, right? Remember that? Remember we did that in calculus, that if you take the first derivative of displacement, it's velocity. The second derivative of displacement is acceleration. The first derivative of the velocity is acceleration, if you're doing velocity, okay? So let's do this. Let's shift it over, okay? And let's integrate both sides. And of course this is going to be t, and again this is as the time approaches 0. And you got to realize something. When the time gets very, very small, then acceleration becomes constant. When you start getting towards time, looking at constant acceleration, how can you have constant acceleration? When the limit of time approaches 0 or gets infinitesimally small, then you can have constant acceleration. Acceleration does become constant. So we can do this, okay? And then of course what? We're going to have what? Vf and Vi. And then we just do the integration, y'all. We do the integration. And it becomes what? Well, we know acceleration's constant. It's a constant. So it becomes what? At, t to 0 is equal to what? V, I'm not going to put the V, final initial. And then we finish the integration, don't we? So it winds up becoming what? At minus 0 is equal to what? Vf minus V initial. Well, look at there, y'all. Look what you wind up with. Isn't that wonderful? So there's doing calculus. Okay. I'm just showing you calculus derivation real quick, okay? Okay, now, that's one. Let's go to the next one. Let's take that same equation. Make sure I'm looking at it right, yeah. Because I had to write all this down. Woo! I wrote all this down, y'all. I had to write it down. And we'll just say V is equal to VI plus AT, right? Okay. Alright, now. Alright, y'all, how do we get velocity? It's the derivative of what? Displacement. Alright, so let's do that. dx over dt is equal to Vi at, right? So, let's take the derivative of displacement. Let's take the integral, both sides. And again, we're going to do it with what? X final to x initial. And this is with respect to time, t to 0. And we got to do dt. Whoop, about to forget that. dt. And of course, acceleration is our constant, because remember, y'all, constant acceleration is constant. And of course, we take the derivative of dx with the derivative, or the antiderivative is what? dx is x. The integral of dx is what? X. So it becomes what? X final to initial. Oh, I forgot to, what did I do here? I made a boo-boo. I forgot to show you the next step. Sorry, somebody should have said something. It becomes dx final initial, that's x final, x initial, is equal to, there we go. Sorry about that. Some of y'all were wondering where I was getting some of this crazy stuff, and that's a plus at. dt, we carry the dt to the other side. Now we got it right. Then it becomes x final initial is equal to, all right, VI, let's see, I don't leave a step out. Yeah, VI t plus A over 2 t squared, right? Because when you take the derivative, when you integrate with respect to t, it becomes what? dt becomes what? T, and then you distribute to t, and it becomes what? VIT plus A is your constant, t squared, over 1/2, or over 2. Okay? And then we finish our integration, and it winds up being, let me go to the next slide. Oh, I'm just going to go ahead and do the delta. It winds up being this, is equal to VIT plus 1/2 AT squared. And there you go. I went ahead and cut it down, okay? Now the last one's a little bit more hairy. We go back to this equation. A is equal to dV over dt. And let's break that apart a little bit more. All right, how do we get dV, y'all? Well, don't forget now, right? Because remember, the derivative of acceleration from velocity is with respect to time. But if you do it with displacement from respect to time, that's what it is. Starting with displacement, boom, boom. It's the second derivative, right? Okay, y'all, look. Look right here. What is that right there? What's the derivative of displacement with respect to time? Velocity? Okay, watch. Right? Okay, now, let's move the dx to the other side, and you should already see where this is going. And it's I'm going to do it this way, v dv. Let's integrate both sides. And this is going to be with respect to x. And this is going to be with respect to velocity. Whoop, the initial. And then we integrate, y'all. And we wind up with what? I left the V off, final and initial, we know that. And we wind up with this equation, y'all. I'm going to go ahead and abbreviate it. Y'all know where it goes. Okay? You go ahead and subtract it out, and you wind up with that when you're done. Okay? So there's doing calculus. Using calculus, okay? So that's pretty cool how you can take it algebraically and then take your calculus and derive it with calculus. By taking by integrating it. Okay, so the antiderivative. Okay? All right, any questions? Now, am I going to make you do that on test? No. No. I just want to show you. Because and I don't know but what, I mean, I like, really and truly, it's easier with calculus. But if you look at it algebraically, y'all, look right here. It's on the end, isn't it? I forgot. Where's that? There it is. If you look at that graph right there, and I know some of you are saying, my God, I can't make heads nor tails of it. Okay. Remember, y'all, constant velocity. Okay? No acceleration. The area under that is my displacement. Changing velocity, and it's changing at a constant rate, that's acceleration. And if it's changing, if the change is constant, then you have constant acceleration, because it's accelerating constantly. Okay? All right. Okay. Y'all want to work a problem?